couple episodes back, we took a little tour of the room here and took a look at all of the projects that I've got stacked up, waiting in the hopper, waiting for me to do something with. And I asked you guys, what was it that you wanted to see? And by far and away, the most popular request was to see more about these little HP decade counters that I have. Now I have two of these, but this one has an actual display output. So I thought it would be more interesting to take a look at. So that's what I want to do today. I want to take this little HP decade counter, take a look at how it works on the inside, and then maybe plug something into it and see if we can get some life out of the digits on the backside here. So let's hop over to the bench and dig into this thing. I'm excited about this one. I think it should be fun. All right, before getting too far into figuring out what exactly this is and how it works, we need to take a look at where it came from first. And looking in the HP catalog from 1959, I came across the 500 series of electronic counters. And looking at the front of the counter here, I can see something that looks really familiar. And that's actually the decimal counting that we see on the front of the decade counter itself here. And so what this decade counter unit is it's a pluggable unit that goes inside one of these 500 series electronic counters. Now, I don't have one of these counters. I would love to get my hands on one, but they're not cheap and they're not all that common. But I've been doing a little bit of reading around on them, and the way I think it works is that you have a frequency coming in, and the counter essentially enables and it just counts the number of pulses in a given amount of time. And so all of the digits will flash while it's counting up, and then it'll stop at the end of its designated time that it's counting for. And whatever number it stops at is how many pulses there were in that given amount of time. And that tells you the frequency of the signal coming in. And if we scroll down a bit further in the HP catalog, we come across this page. And this is their advertisement for the AC-4 series of decade counters. And if we look at the edge of our decade counter here, we can see it's a model AC-4G. So this is the original advertisement for the model that we have here. That's really cool. And if we look at the bottom of this advertisement, we can see they list three different models: AC-4C, AC-4G, and AC-4E. But throughout the years, they made a lot of different versions of these decade counters. And so there's a whole lot of different ones out there. And so after a bit more searching, I came across an AC-4 series manual, which had a ton of wonderful information in it. And you can see here, this is the specifications for it. And we can see that the maximum counting rate is 120 kilocycles. But what's more important for us to try and give this thing a test is going to be our driving voltage and our power down here. And we can see that our power is plus 300 volts. So it needs quite a lot of voltage. And of course, we've got 6.3 volts for the filaments in the vacuum tubes there. And our driving voltage all the way back up here says a minus 80 volt pulse with a 1 microsecond rise time. And so seeing this minus 80 volt pulse here was a little confusing at first, because I wasn't sure if that meant that I needed to go 80 volts below ground or if it meant something else entirely. And so while these specifications were great to kind of give me an idea of where I was headed, I needed to dig deeper. And so if we scroll down, we start to peel away this onion and realize that there are so many interesting things going on here. So essentially this thing is 4 flip-flops. That's what each tube is. It's a dual triode that makes up a flip-flop. And we'll take a look at the schematic here in a bit. But 4 flip-flops are usually used to count in binary. If we think about binary, if you have 4 flip-flops, that's 4 bits, and you're counting 0 to 15. But if we look at the front of the unit, it only goes 0 to 9, and it uses a very interesting binary coded decimal. Usually the weighting is 1248, but this one uses a weighting of 1224. But just looking at zeros and ones here in this table is a little difficult for me to wrap my head around. So if we scroll down to the next page, we can get a look at what the waveforms are for each of the plates of each of the 4 flip-flops. And we can see that we have an input that essentially is just a low pulse coming in. So it starts at some high level, and then We have a very quick, sharp pulse down, and I'm assuming that's what they mean by a minus 80 volt pulse. And then it comes back up to the high level. And each time there's a pulse, we can see that the plate of V1 flips state. So this is actually exactly what we would expect in a normal binary system. But where it gets interesting is the plates of V2, V3, and V4. Now, to understand why these are so interesting and a little weird, it would be best to compare them to what we would expect out of a normal binary decade counter with a weighting of 1, 2, 4, 8. So let's take a look at that right quick. So here we've got a comparison of a 1248 and a 1224 binary. And I've actually flipped the little charts over here on the left around so that the least significant bit is on the far right and the most significant bit's on the far left, because that's just how I'm most accustomed to looking at it. And if we look at the waveform for the standard 1248 binary setup, you can see that we have a clock signal coming in, and then we've got 4 signals after that. And each one of those 4 signals is half of the frequency of the one before it. But if we look at the 1224 binary, we can see that the first signal looks pretty much exactly the same. It's a divide by 2, but the second, third, and fourth signals get weird. And on the second signal, you can see that where it would normally transition back to low, we have a low spike, but then it comes back up and stays high for another 2 cycles. And we see the same thing again on the third signal and the fourth signal. Now, there is something to note that at the far right, it shows all 4 of these going low again. And that's because once we get to 9, it actually just resets itself back to 0. And that's just the way that the chart was drawn on this, because we're only trying to count from 0 to 9. But this weird low spike and then staying long is really wild to me. It seems to go against everything that I've learned about counting in binary. But that's the way that they designed these flip-flops to flip in order to give them the 0 to 9 decimal output that they were looking for. This kind of weird waveform is not the only interesting waveform that's going on inside of this module. If we take a look further down in the manual, we come across this page of all the waveforms. And from top to bottom, we can see, we've got an input coming in, and then we have the V1, V2, V3, V4 plate. These are the plates of our 4 vacuum tubes. But it's this staircase output on the bottom here that I find most interesting. Depending on which decimal digit we're at, the output voltage on the staircase output pin is different, starting at 138 and going all the way down to 54. And it looks just like a staircase. So when we fire up the module, we're going to take a look at this as well. I think that's going to be really cool to see on the voltmeter. So we have a basic idea of the signals that are moving around inside this unit that are resulting in a count from 0 to 9. But how exactly is it doing it? Well, there's really only one way to find out, and that's just to look at the schematic. So let's take a look at the schematic for it right quick. Now, this schematic is really interesting because the scan came from somebody who was working on these or something, and they left a bunch of notes. So we kind of have to read around whoever's notes these are, because they are definitely not my notes. And it looks a little overwhelming at first because there's lines going in every direction. And that's because it does really interesting things in the way that it illuminates the neon bulbs over here. Because it's not a simple binary on-off. They're actually adding voltages together to turn the neon bulb on or off. So you can see in the condition that it is demonstrating here, it's currently set to 0. And you can see they're showing that by showing these cute little lines coming off of the neon bulb here to show that it's illuminated. But there's plus 137 volts on one side of that neon bulb and plus 75 volts on the other side of that neon bulb. And it just so happens that that's enough of a voltage difference between the two to illuminate the neon. But the other neon bulb that's right next to it still has plus 75 volts on one side of it, but on the other side of it, it's plus 110 volts, which is not enough of a voltage difference to cause it to illuminate. And if we look at the rest of the neons, we can see plus 135, plus 95, plus 95, plus 95. And what this is doing is it's keeping the voltage potential difference between the essentially cathode and anode of the neon low enough that the neon doesn't strike. And then as the flip-flops change states, this kind of voltage potential difference also changes states as well. And so the triodes are turned on by a weird collection of plate voltages being fed into the different parts of the neon bulbs to create this really complex but ingenious way of selecting which neon tubes are indicated based upon the binary that's stored in our 4 vacuum tubes here. So let's zoom in on one of these flip-flops and take a look at it and see what makes it so interesting. And fortunately in the manual, they have a really great explanation and a boiled down illustration of how the flip-flop works. So there's a couple really interesting things happening. We can see that there's a plus 300 volts coming in, and that's our common plate voltage. And you can see it comes in through a 47K resistor and then splits and goes through 2 individual 47K resistors, and then after that it goes directly to the plates. And then coming off of each plate, we have a 270K ohm resistor and a small capacitor feeding into the grid of the opposing triode. Now what's interesting here is that when one of these triodes is conducting, the plate is pulled to a lower voltage. So we can see here that triode B has a plate voltage of plus 53 volts, and triode A has a plate voltage of plus 135 volts. So triode B is conducting and triode A is in cutoff. Now to get it to flip states, instead of acting directly on the grids, we actually interrupt the plate supply voltage. So on the input, we go through a coupling capacitor here. And when we hit our minus 80 volt pulse, we essentially break off the plate voltage that is making it to the triodes themselves. But what keeps this from just staying in the same state it was at are the 2 capacitors that go to the grid, C2 and C3. Before we sent our input pulse in, these 2 capacitors were actually sitting at 2 different charge levels. One was sitting at plus 135 volts and the other one was sitting at just plus 53 volts. And so as the plate voltage comes up, the differing voltage of these capacitors causes the opposing triode to start conducting, causing the entire system to flip states. Now, once the states have flipped, the voltages at C2 and C3 are now also flipped. So the next time we send an input pulse in, the flip-flop flips back to its original state. This is a wild way of doing this and something I never would have thought of, but it's really brilliant. This is really cool. And so in order to test this out, it just so happens that there was a page in the manual that talked about building a test circuit for it, a little triggering circuit that allows you to test it outside of the system. Now this setup looks fairly simple, but there's a couple things that I didn't have. I didn't have a switch that had a normally open and normally closed contact like this. And I also didn't really care about setting up the reset switch over here because I was just going to pull the reset to ground. And so after a little bit of work, this was the triggering circuit that I came up with. So you can see over here on the left, we've got our 2 power supplies. We've got plus 6 volts, which is obviously for the filaments, and then we've got plus 300 volts, which is a large amount of voltage. And then all the way over here on the far right are 5 of the 6 pins that we need to hook up to just get this thing powered up. And then right here in the center is my overly simplified schematic for getting the triggering to work. Now I'm using a voltage divider here of 330K and 220K off of 300 volts, and then it goes through a 1 meg, just like in the original triggering schematic. And then I have a little switch here that just essentially pulls that to ground. And then we have a small capacitor and a small resistor with our input coming right off the center of it. And this is really similar to what the triggering circuit is like in the manual. I just simplified it a little bit and threw in some of the values that I had sitting in the drawer. So hopefully it'll work. So let's pull out the actual unit, put some power on it, and see what happens. All right, we've got our HP unit set up here. Now it's sitting on the table upside down. You can see we've got 0 at the top and 9 at the bottom, and all of the numbers are upside down. And that's because the plug is on the bottom side of the unit. So I have to flip it upside down in order to get all my alligator clips onto the correct pins. And here's my breadboard with my triggering circuit on it. I have 24 volts coming into the main power rail on this side, and then I have 2 of these little cheap regulators that I got on Amazon. And this one goes from 24 volts down to 6 volts for powering the 4 filaments. And this big one on the right goes from 24 volts to 300 volts. So there is 300 volts on this primary rail down here, which is I don't recommend putting 300 volts through a breadboard, but the currents are so low that so far I haven't seen any bad things happen. But let this be my official statement of do not try this at home, even though I'm literally trying this at home. But I think we should just power it up and see what happens. So we'll go ahead and flip the switch here. All right, the power supply is on. Oh, yeah, look at that. We've got the number 6 illuminated here, even though it looks like a 9 because the unit is upside down. So this little button right here is my trigger. So let's push that button and hopefully we'll go up to the number 7. Yes. Look at that. We went from 6 to 7. So every time I push this button, it should advance 1 digit. There's 8. There's 9. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and back to 0. Awesome. We did a full run down the entire option there, and it's working perfectly. So this random impulse buy that I got off of eBay is perfect. The vacuum tubes still work great, and they're the original HP tubes from like 50 years ago. All of the resistors and capacitors inside are still functioning exactly like they should. I mean, this thing is awesome. It's such a beautiful demonstration of the type of engineering prowess that HP was capable of. And you gotta remember, this is just one tiny little piece of a much larger system. And so the frequency counter that this was installed in has got to be one of the most exquisitely engineered pieces of machinery out there. But there's one last thing that I want to check, and that is the staircase output voltage. And if we remember, the waveform showed it looking essentially like a staircase. As we move through the digits, the voltage on that pin should change in small steps. So I've got my vacuum tube voltmeter here, and so as I push the button and this changes position, we should see the voltage change on here. And right now this is set up for the 300 volt scale, so on the far right it's going to be 300 volts and on the far left is 0 volts. So let's go ahead and flip the power on, and once this unit is stabilized, we'll push the button and see what happens. Yeah, look at that, it jumped all the way up to 225 volts. And there we go, there's 100 volts that it's sitting at right now. And we're at number 6 again. So it seems that the vacuum tubes here kind of like to warm up right around this area. Very similar to my vacuum tube computer that likes to initialize into the same state every time. So that's pretty interesting. All right, so I'm gonna go ahead and just spam the button real quick to get us down to 0. So on the vacuum tube voltmeter here, we're reading right around 140 volts. And if I look back at the page, that looks right because it says digit 0 should be at plus 138. All right, so that's a good sign. That's a good indication. So let's push the button and go to 1. Yeah, we dropped just a little bit of voltage. Then 2, 3, 4, 5, 6, 7, 8, and 9. And 9 dropped us all the way down to what looks like 55 volts. And if I look back in the manual, 9 should be at plus 54 volts. So not only is my vacuum tube voltmeter reading pretty much spot on, this staircase voltage is working beautifully. How cool is that? So not only do we have the indication moving down the front of the face exactly as it should, our staircase voltage is working perfectly as well. Hewlett Packard engineering just absolutely floors me. It is impeccably built, impeccably designed, works amazingly well. Even after 50 years, this is still just a wonderful working machine. I am so glad that you guys wanted to see more about this because it allowed me to really dive into it and learn a lot more about it. And it has made my respect for HP just go through the roof. They built some phenomenal equipment, and that is evident even in such a small, tiny component of a larger system. So thank you guys so much for watching. I had an absolute blast digging into and learning about this, and I hope you guys enjoyed it too. So thank you, and hopefully I'll see you in the next video.